So now that I've given you an overview of object-oriented and functional programming, let me go ahead and do a little deeper dive into some of the key concepts and features that are part of the functional programming aspects of Java. And all of the features we're going to talk about here were added in Java 8 and or beyond. The bulk of them were added in Java 8. There were little tweaks and enhancements that were done later. So we're going to focus largely on the Java 8 parts. And that's also relevant because those are the features that Android supports. Android does not support the later versions of Java. And I'll also compare and contrast functional programming with the more traditional object-oriented programming we've talked about. So functional programming actually goes back a long way. It has its roots in a formalism called lambda calculus, which was developed a long time ago. And so it's got a good foundation mathematically. And basically what it says is treat computations as the evaluations of mathematical functions. So you have some input that's passed, which could be several parameters that are passed to a function, and that function then generates some output. And as we'll see, it should have no side effects other than to produce an output result. So ideally, each function in functional programming should be a so-called pure function, and that's just a fancy way of saying it doesn't have side effects, like it doesn't store things in memory that's mutable. It doesn't write things to a file. Now, it turns out in practice, this is sometimes a little too difficult to enforce because we do have to do things like store things in files and read things from files and store things in memory and read things from memory. But as much as possible, we try to eliminate that. And we'll talk about that as we get a little further along. One of the other things you can do with a functional programming model is you can compose the functions together. So the output of one function then is connected to the input of the next function. And this forms what's often known as a pipeline, where you can pipe things together. If you program very much with the Linux or Unix shell, or even the DOS or Windows shell, you're familiar with the concept of redirecting standard input and standard output and putting them together in a pipeline where the output of one program flows in as the input to the next one. Same basic idea with functional programming. In fact, when we start talking about Java streams, you'll see that this is the very idea of Java streams. You connect things together in little pipelines where the data flows through these transformation or filter operations. Here's a very, very simple example of this. This will compute the nth factorial in parallel. So what we're going to do is we're going to compute the n factorial, and we'll see here, you can actually go to my link. You can actually go to my GitHub repository and click on this link, and you'll find the example that demonstrates what we're about to walk through at a high level here. So what we're doing here is we're going to generate a range of values from 1 to n. Let's say n is 8, just to make it simple to fit onto one slide. And then we're going to go ahead and split up that input sequence into little chunks. And then these little chunks are all going to run in parallel. And what we're going to have is each of these little chunks will run sequentially to do multiplication of values pairwise. But all these things are going to run at the same time on different cores. So we're going to multiply 1 times 2 on one core. We're going to multiply 3 times 4 on another core. We're going to multiply 5 times 6 on yet another core. Multiply 7 times 8 on yet another core. And all those things will take place in parallel. And then we're going to have this final stage called the reduce stage, where we multiply everything together and we end up doing what's called reductions, where we take the results of 2 previous stages, multiply them together to form a single reduced result, and we keep doing this until we have just a single result for the entire factorial. Now, this may or may not make much sense yet. By the time we get done talking about streams and parallel streams, it'll make a lot of sense, and you'll get a lot of chance to play around with it in practice. So what we're doing is we're combining these values together, and we finally end up with a single result. And we can do this very nicely in parallel, which takes good advantage of modern multi-core processors and the ability to optimize things that run in that fashion. So we're basically streaming stuff through and doing the computations in parallel. In order to avoid all kinds of hazards with parallel processing especially, we try to avoid sharing mutable state. We try to avoid having side effects. So changing state, changing data, especially changing data that's shared between threads, that is to be minimized or avoided altogether. To show why that's important, here's another bite at the apple of this factorial example, except this time it's got a big bug in it, just to show you what can go wrong. So here we go ahead and we allocate a new object called T of type total. You can see total over here. Let me move my head out of the way. You can see that total is got a field called M total. It is initialized to 1. And it has a method called mult, which will increment M total by multiplying it by N, which is the parameter passed to it. That's what's called shared mutable state. And it's shared mutable state because we're going to run all these multiplications in parallel using the parallel streams directives. And the problem here is that the various multiplications that update M total will all occur at the same time. And because they're not synchronized, that's going to lead to something called race conditions. And race conditions are basically corruptions of data when multiple threads try to read and write to the same location in memory in a non-synchronized or non-atomic way. And these problems are really tricky and pernicious to try to deal with. So we'll talk a lot more about those. In fact, one of the things you'll learn about parallel processing in Java is you avoid race conditions often altogether by not sharing mutable state. This particular example has bugs. It's got memory visibility problems as well. So the long and the short of it is this code is not going to work properly. And you can prove that to yourself by running the example on a multi-core processor and seeing that it gives garbage results. You have to know how to avoid these problems. Java, the language, won't solve them for you. The Java execution environment, like the Java virtual machine or the Android runtime environment, will not save you from these problems. Only you can solve them by knowing the proper patterns and features in Java to use and Java's class libraries to use to program correctly. This class will give you one slant on how to do that by avoiding sharing state pretty much altogether. I teach another course that some of you have already taken on concurrent object-oriented programming with Java, which teaches you how to use synchronization mechanisms to avoid these problems. That's for another time though. So rather than using the shared mutable state, which gets us into all kinds of trouble, what functional programming features in Java do is they focus on so-called immutable objects. And immutable just means once they're assigned, they can't be changed. So after the object state is set by its constructor, then it cannot be modified any further. Now that seems a little esoteric at first until you realize you've probably been doing this for a long time with Java, because Java has this thing called a string. And you can see again here the way this works. Let me move myself out of the way. The Java string class does not allow changes to a Java string once it's been set by the constructor. So the constructor sets the values, and then none of the other methods can actually modify the state after the string has been initialized. So that makes it immutable. And you can learn more about that if you read the link down here. All the fields are final, and there's only accessor methods in the Java string class. And there's lots of other classes now in Java that work that way as well. So let's talk a little bit about functional versus object-oriented programming. So in contrast to functional programming, which tries its darndest to avoid state, especially shared mutable state between multiple threads, object-oriented programming employs something known as hierarchical data abstraction. And you've probably seen this. I'm sure you've done this before in Java classes, perhaps without realizing it. But if you take a look here, we have something like the Java iterator interface, which then has to be implemented through effectively subclassing in order to fill in the various methods it defines. And the way things work with the object-oriented part of Java is you think about your components as being based on stable class and or interface roles and relationships that can be extended using inheritance and dynamic binding. So you start out with an interface like the Java iterator interface or a component node interface or whatnot, and then you go ahead and extend it through inheritance and dynamic binding in order to be able to provide the imperative capabilities to modify the program state as it runs. The way in which you design things in object-oriented programming is not around algorithmic actions implemented as functions, but instead in terms of classes with well-defined stable APIs. To the extent that you have state, and you typically do have state in object-oriented programs, it's encapsulated by methods that perform imperative statements. So for example, if you look at the iterator abstraction that's part of Java and has been since day one of Java, then it's got a couple of methods like has next and so on. And these methods encapsulate the state. So you don't know how it's implemented under the hood in order to use them. However, they will access and update the internal iterator state. So they are still imperative. They still make modifications to that state. And that's why you have to be very careful not to use iterators in multi-threaded programs, because bad things will happen. Chaos and insanity will ensue. So that's just a quick overview of some of Java's functional programming concepts and features. Do not fear, when we come back starting on Wednesday, I will go through other features in great detail. We will talk about lambda expressions. We will talk about method references. We will talk about functional interfaces. And these will give you all the things you need to do in order to be able to complete all of assignment 1. The first part of assignment 1, however, just focuses on the object-oriented parts, just to make it easy to get started.